Greetings. I am here to carry out an example on the Hooke's law simulation that you would find in the FET simulators of experiment. Now, the type of selection, first and foremost, you must ensure that when you go to the mass and spring activity or simulator, you must select lab. Okay, that's the section that we're using. Now, in ensuring that you understand what you're doing, it is always important that you bring up your S.B.A form. Okay, so this is done in collaboration with a Google form. All right, now let's just put in my name there. Okay, if you do not know where your link is in this experiment, the link was placed on the form. Now, a diagram showing the laboratory setup for Hooke's law. Good. That's it for me there. All right. Set up the apparatus as shown in the diagram. Measure the original or natural length of the spring by laying it down, and measure the length with the spring. Stretch out, but not pulled, to produce tension. This length will be the distance from that starts from the first coil of the end and lands on that, and that, and record its value. Now securely attach that lower this. Now securely attach one end of the spring to the clamp and stand vertically and our bench. So what you're understanding all of this, what it is saying is basically it is saying what you're seeing in the diagram. Good. Now what is in the diagram is not how it's set. We do not have a scale, a carrier pan for the mass. All right, so our 50-gram mass will act as our our scale pan first. All right, because in this experiment it is said that we would add the scale pan and then we would have recorded that. All right, now repeat. So attach the mass carrier to the lower end of the spring. This counts as the first 50-gram mass on the spring. Record the position of the lower surface of the carrier along with the rule denote this reading of the stretch length by L1. Sorry. Record this value of the table in the Google Docs. So see, we have our Google Docs. It is open here. We had gotten it. So in this case, the teacher had uploaded it here. All right, you go here, you'll find the doc here, and you'll find information on the Jamboard there. Now, moving forward, they say you should have carried out a dry run, then unload. So this was to ensure, if you notice, there's a precaution there, right here. There's a precaution here. All right, there's a precaution there. Here's an next precaution here. So we should be able to add our precaution. The teacher might upload source of error, a section for source of error and precaution. So if you should go back and see source of error precaution, that is a possibility that the teacher could add that right there. All right, now this is the important part. Now start loading the spring. All this was precaution also, as this load of 0, check to see whether the spring, all these are what you would have done if you were carrying out the experiment in a real life situation. All right, by reading this, you know some things would not have applied to the simulator, since the simulator is being done virtually. All right, but just to give you a feel of what it would be like in the lab, you would have get a sense of what it would be if you were setting it up. Now this is where we are. Now start loading the spring once more from 50 gram by adding mass to the mass carrier in steps of 50 to increase the load or the tension of the spring. Each time the mass is added, note the position of the carrier along the ruler. Record the value of the load and the stretch spring L1 in the table. So basically we're saying we're just going to load. So here's the table. Now it is important to note that something is missing here. So you need to copy this, copy it, times 10 to the minus 2. All right, that's it right there. So you can make the corrections right there. All right, now so we know that would have been in millimeters, but if you notice here, the reading is in centimeters. All right, the reading is in centimeters. So correction, this is times 10 to the minus 2, so this is centimeters. So the centimeter is on the rule. And even though it says millimeter here, you know that all readings that are taken should be in, okay, it didn't say millimeters here. All right, it didn't say the millimeters here, so that's good. Originally it would have said in most cases millimeters, so it did not say millimeter. So right here it says centimeter, and we know that centi is times 10 to the minus 2. Okay, just highlighting these things so that we know what we're doing. Now what you want to do, you want to set up, so for the same, you want to know how to identify the original length. So no matter how much I move this up or down, there's an original length right there. And from our experiment, from the write-up in our experiment, we know that from here, the first coil, to here, all right, so we're looking at approximately 45, 47. All right, so we're looking at 47. All right, we're looking at 47. So if you look, it was already there as 47, Good. So what you want to do now, when you do your calculation here, you should know that, all right, you check if it is 47, so you're good. As you can see, it is 47. The mass equilibrium, you can put that, it's not needed, but it can be put there. And the movable line, this is important, all right, because this can be our marker when things are moved, when you move the ruler after reading. So let's go at our first 50. All right, now what I want to do, I want to measure here, then carry down it right here, and I'll say, all right, that is approximately, let's see, I was at 50, I have passed 50. All right, so this is 55, 56, approximately 56. So this is 56. All right, so this would be 47 minus 56 minus 47, sorry, 56 minus 47, and that would give me that. All right, and you want to continue that, so say let's skip here and let's get to 300. all right, let's get to 300. all right, so let's allow that to oscillate and settle out a bit. all right, let's see how far it's going to go. So while that is happening, you want to note a few things. Acceleration due to gravity is preset to that. Note the spring constant. It is more than likely that these things are going to come out at us. All right, the spring constant. All right, now so let's say it's still moving. So another source precaution, you must allow the spring to come to complete rest before you take any reading. So here I'm looking at 90, 95, 91, 92. Let's say approximately 92. So for 300, all right, we're looking at 92. all right, 92. So this would be 92 minus 47. all right, so what we have done here is I've skipped out this. all right, you will be doing that for yourself. all right, you'll be doing this for yourself, so I encourage you to skip that out. Good. And what you want to do, you should know how to convert from kilogram to load. all right, and you must show a sample working. all right, I will accept W is equal to mg. I will accept 1 is equal to mg. So therefore mass, which is let me just get this down here. So that is 50. all right, 50 times 10 to the minus 2 kilogram. all right, and that multiplied by 9.81. that's what we're seeing here, 9.8. all right, 9.8. all right, meter per second square. Alright, and then your answer for that will go there. Good. And then you would have that. Okay, so after you get your results, you will notice that this is not a very tedious experiment. After you get your results, all right, let's see if, all right, when you get your results, you would notice what you will notice is that you are asked to plot a graph. You are now asked to plot a graph. All right. Please do remember that each time you do a lab, an experiment, you are expected to have your graph paper working with. Please, you're expected to have your graph paper working with. All right. Let me see if I can help you out with a graph. It's going to be just a sample. Okay, it's not going to be accurate. The values are not real. It's just for explanation's sake. Please do not use the values that you see, because these are not real. All right, this was just set up for you to have an example of what is going on. Again, please do not use these values. They are not real. They are just for you to have an understanding of the graph and what it should include. So your graph will have its title. All right, and so when you're making up your graph, always ensure, you will soon see it on the screen, you should ensure that it has a proper title, which, all right, title of graph. I will not put a title, because even though I know you know that you're not supposed to, I know you know that you're not supposed to use what the same exact thing as I am using. I am going to ensure now that I make your life a bit easier by not putting you in that situation where you're tempted to do so. All right, so let's read what our graph is supposed to be. Our graph, we're supposed to plot here, now plot a graph, F, force against mass mean length, force against mean length, and they say it should be mean. So what I'm going to do, all right, this will change because the reading was taken in centimeters and that millimeters, so that will change. All right, so moving forward, we have force on the y-axis. That's what we're working with. Force is on the y-axis, so force is on the y-axis, and the Newton there, force is measured in Newton, and we're having the mean length on the x-axis, and that is measured in meters. Where you do, yep. So I'm just setting up the graph to carry it over for you guys to see. Let me just put in the grid lines here, put in the grid lines here, put in some more grid lines there, let's put in some more so that you're about to see it in a few. Alright, grid lines, grid lines, grid lines, the one last one. Alright, so that it looks as close as possible. Alright, where we're putting it, so we're coming over here. Alright, now when you know you will be drawing, and remember each calculation, remember that you should have your units in your calculations. Alright, so for this graph here, let me put in something before I paste it. Let me put in the line of best fit, so no one can say but sir. Alright, no one can say but sir, so that when you put in the line of best fit, let's copy that and come back over to here. Alright, now this graph is a computer simulated graph, so it will try to plot the graph as to the line of best fit, but you would go through 0 from origin. Alright, try to get it from origin. Alright, there are some teachers who accept as it is right here, and there are others that do not accept. They want you to go through origin so that you can get the most appropriate line. Alright, now with the Hooke's law, you should get a straight line graph. Alright, now the line of best fit starting at origin, notice how close, not all the lines are on, all the points are on the line, sorry, not all the points are on the line, but most of the points are near the line. That's what we call the line of best fit. It is best drawn with all its points very close to it. Alright, remember this axis is not, these values, these scales are not supposed to be used. These are just for my example. Alright, so you must make your own scale. You must make your own scale, and that would come from your information that you have gotten right here. So this information here, right, this information here, mean extension, this information here, so you'd have mean extension or mean length, mean extension or mean length. Right, this is on the x-axis, and this is on the y-axis. So it is very important that you make your scale. This is on the value here is on the y-axis, and the value here is on your x-axis. So if you do your calculations and you get the wrong values for your load, then you know your experiment is going to be incorrect. All right, now let's see what after we draw our graph, we are expected, if your graph is a straight line through the origin, then it shows that the load applied is proportional to the extension produced in the spring by that load. All right. Now, that is Hooke's law right there. That there is Hooke's law. All right. Now, there are some housekeeping things that you're encouraged to do. You will be seeing some more information coming on how to treat your your results. All right. Now the discussion. All right. In your discussion, you will be discussing these questions. You'll be discussing your discussion might be based on the answer of the following question: were there any condition that arose which made it difficult to proceed, or which gave rise to reading error? 1. Could the two set of extension obtained have been used in different ways? If so, what is that way? Which method of treatment would be better? Why? The information for this is in your textbook. For CXE students, it is in the Physics for CSEC 3rd edition, the Macmillan, published by the Macmillan Publisher House. This experiment is in the book and it is explained in detail there. All right. Now, for us, what you'll notice, you find the gradient of this graph. You will find the gradient of this graph. Now, the gradient of this graph, remember, f is equal to kx, right? And if the gradient is f, the gradient is f divided by x, then you would have found your spring constant there. Okay, you could have found your spring constant there. Now your teacher will provide you with additional information for your discussion also. All right, you must work out your gradient and remember, in drawing your graph, it must be as large as possible. You could turn your graph paper sideways so that you can get maximum. You want your points, your y-axis points, to be as large as possible. All right, you don't want to be drawing a graph that takes up from 0 to 8 and from 0 to 6 that small. No, because what you're going to do, after you draw that big graph, you want a very large triangle so that you can make you can make your calculation, your gradient calculation, as accurate as possible. The larger the triangle that you obtain from your graph to get the rise over run, all right, that's the most accurate your answer will be. Okay, so that's basically the Hooke's law S.B.A result, just in a nutshell. And this is taken from the Physics 3rd edition, the Macmillan. If there is any concern, you can reach me at Golden Genius at gmail.com, and I will sure to assist any question relating to this experiment, S.B.A. experiment, or any related experiments. Thank you very much for viewing this video.